So, we have done all the physics of transistor operations, and let me revise. So, we had this transistor, our favorite transistor NPN. So, here we have a resistance RB and then a biasing. Emitter is common. From collector we put this RL and then we have the biasing here. This is the basic circuit. And then you know there are three regions of operation. One is known as cutoff, one is known as active, and one is known as saturation. And cutoff means this biasing voltage here in the base circuit is very small, or there is no biasing, so that this base emitter junction is not forward biased or not sufficiently forward biased. In that case, there is no injection of charge carriers from the emitter to the base, and therefore no current anywhere, and that is cutoff. It looks trivial, but yes, it is important. Then we have active region. If you have sufficiently forward biased base circuit, this base emitter junction is sufficiently forward biased, there are a lot of electrons which are injected from here to here, and the collector is also sufficiently reversed bias. This collector base junction is also sufficiently reversed bias, so that when the electrons are injected, a good fraction of that decided by beta, that much is taken up by this circuit, and then you have a current. So, you have a current of IC here like this, current of IB here like this, IE, and then you have IB which is going like this. So, this is the normal operation, and that is the active region. In active region, if you increase this biasing voltage here little bit, if you increase this biasing voltage little bit, there is more injection of electrons, and the collector is also sufficiently reversed bias. So, if there are more electron injection, then this also proportionately draws more electron, and this IC also changes in that same proportion. So, that is the region of amplification. When we use transistor as an amplifier, we are in this region. And then saturation. Saturation means this is forward biased with a good biasing voltage, so that a lot of electrons are being injected, and the collector is not ready to take those many electrons. So, its capability of drawing electrons is saturated. In that case, you have saturation where IC does not increase in that same proportion in which this IB increases. So, if you draw a graph of say output voltage, this is our output voltage VO, this is 0 voltage ground which we call. So, if you draw graph between this output voltage here and this input voltage here that you are applying VBB, that we are applying this voltage, which you can call VI input volt. So, if you plot this graph here, what happens? If this VI is very small, you are in cutoff region, and if you are in cutoff region, this IC is 0. If IC is 0, no drop on this RL, and therefore, whatever voltage is here, same will be voltage here. So, this battery voltage, that will appear as this output voltage. And if you increase it slightly little bit, it is still not forward biased with sufficient strength, and it remains in cutoff region. So, you increase this VI, and initially this will remain at V0. So, that is the cutoff region, and then starts active region, in which you have a biasing voltage which is say more than this, and then the electrons are there, electrons injection starts, and then those electrons are being drawn here IC appears. Once IC appears, there is a drop on this RL, and this voltage, this output voltage decreases. So initially it will not be proportional, it will go like this, but then it will become linear. So that the change in VO is proportional to change in VI. Okay, and that is the voltage gain. So this is that active region, and then once you have lot of VI, then the injection is so big, the charge injection, carrier injection is so big that this is no more able to draw the current, increase the current. So the current remains at close to that maximum, and therefore the voltage drop becomes constant and very close to 0, like this. So this is saturation region, this is cutoff region, and then this is this linear part is active region. These are the things. This we called, this we talked. And then in the active region, in this the linear region, if you increase VI, then this VO decreases, but there will be an amplification. A small change in VI will lead to a large change in this VO, and that is the amplification, that is the voltage gain. Voltage gain delta VO over delta VI, which is minus beta times RL over RB. So this is RL and this is RB. So these are the things. So today's agenda is to perform this circuit on the table, to take a real transistor, batteries, biasing, resistances, do this circuit here, measure the values and see where are those 3 regions, and then if time permits, about amplification. So, but today's mostly we will concentrate on this cutoff, active, saturation regions. Okay, before that we have to change this VI. We have to change this VI, and then we will see all those regions. So how do I change it? So what we have done in our experiment is the following. We have taken a long heater coil, a resistance in fact. This is a resistance, and then on this resistance we are putting a 1.5 volt battery or cell, like this. We will be putting a switch here, or we will be connecting it at the time of actual measurements, but in the diagram I am showing it connected. So this is 1.5 volt cell, right. So the total drop from here to here is 1.5, and this negative we will take as the 0 potential. So this is actually connected to this ground. So you see the emitter terminal, negative terminal of this battery here, and then the negative terminal of this battery here, they are all connected together, and that is called 0 potential, and that we call earthing or we call grounding, like that. So in the circuit also, that will be we will be adding, we will have all these negative terminal here, this emitter, everything will be added at one place, which we will call 0 potential. Then the biasing will be given, by taking a variable point and touching it here or connecting it here. So what voltage I am applying here? I am applying the voltage which appears on this part of the resistance, or this part of the resistance. This is 0, this is 0, and then this is at some VI, and that same VI is here. So this will be our VI. So this is how we will be making a variable biasing volt. This, if I put it here, then the voltage appear will increase. Suppose I put this terminal, this variable point here. In that case, I have increased this biasing voltage. So in this curve, I have gone towards right, okay, because now this much of voltage, this much of potential difference, that is getting applied here. So this is one part. Then the values of resistances are, here we will be taking a 120 kilo ohm resistance, and this RL we will be taking 10 kilo ohm resistance. This is 1.5 volt. This we will take a 9 volt battery, which may not be 9 volt, it may be 8.9 or 9.2 or something, but to what is called 9 volt battery, so that we will be using here. So these are the values that we have to, so keep this circuit in mind. Keep this circuit in mind and see how this circuit is being assembled here, and follow each step closely to see that okay, this is how things are connected, and then we will make measurements. Measurement of what? Measurement of this VO and measurement of this VI. So to make the measurement of this VO, we will take a multimeter. We will take a multimeter. Multimeter also has two terminals. One terminal is black, one terminal is red, and then black one is supposed to be connected to that zero potential. So we will be taking lead from here, and that black terminal will be connected to this 0 point, this line here, this line here. So it will be connected to this, and here the other terminal will be connected here, so that it can measure this VO. Similarly, we have to measure VI, so we will take another multimeter. And here also you have black terminal and you have red terminal, and the black one will be connected to this zero line, this zero voltage line here somewhere, and this red one, which has to measure VI, should be connected to this point. So this will be connected to this point. Okay. So this is measuring this voltage, and this is measuring this voltage. So this is the circuit. Keep this in mind, and now we start the experiment. So we have put everything on this table, the multimeters, the transistor, resistor, connector, connecting wires, batteries, everything here. And this special thing here is called breadboard, and all our circuit will be designed on this breadboard. So let me first tell something more about this breadboard. In this breadboard, you can see there are so many holes here. You can all see this is a hole, this is a hole, this is a hole. All these are holes. There are some holes here, there are some holes here. So too many holes are there. Here you can see there are 1, 2, 3, 4, 5 holes here. Then on the same longer line, you have 5 holes here, 5 holes here, 5 holes here, and so on. So all these 25 holes on the upper line, this 5, then this 5, then this 5, this 5, this 5. All these are connected to each other internally. Similarly, if you go for this next line, there are 25 holes there, 5 here, then 5 here, then 5 here, then 5 here, and then 5 here. All these 25 are internally connected to each other. And similarly is the story on the other side. And similar is the story on the bottom side. Here also all these holes are internally connected to each other on one longer line. All these holes are internally connected, and similarly on the bottommost line, this line also, all these 25 are internally connected to each other. That's it. And similarly for this side. Now come this central blocks. So here in the central block, the holes which are along the width, this one, then on the same line this one, this one, this one, this one, they are all connected to each other. Similarly for each of these lines, which are along the width of this rectangle, these 5 are internally connected, these 5 are internally connected, these 5 are internally connected, but one line and any other line, they are not internally connected. Similarly here, this one line and this other line, they are not internally connected with each other. So keep this in mind when we perform the circuit. So, now Ranjit has to help me. So, as I said, you have all the negatives of the battery, the black terminals of the multimeters, the emitter, they are all connected to zero potential line. They have to be connected to each other, which we will be calling zero potential. So, on this breadboard, I will be using this line here for that zero potential thing. They are all connected to each other. So, let us put 5 connecting wires in which we will be adding our zero potential points. Very good. These are all connected to each other. Internally, they are all connected to each other, and therefore, they are on the same line, same potential. So, let us first construct that input side and the 1.5 volt battery with heater coil to give bias to the base. Right. So, this is that heater coil. On this, we will be putting 1.5 volt of the battery. So, 1.5 volt you can connect here, positive here and negative here. Do not connect it, but keep it close. Positive here, yeah, positive here. And this we will be connecting to this point when the actual circuit is ready and we will be taking readings. That time we will connect it here. So, this is a kind of switch. I put it here and it is on, I put it here, it is off. Okay. So, this is one part. Now, let us put the transistor. So, this is the transistor. I had shown you earlier. This is a transistor, and if you look at this part here, this is flat part. This is flat part. So, keep this flat part towards yourself. If I rotate it, you have this round part. On the other side, this is round. This is round part. So, keep the flat part towards yourself. Then what is on the left is collector, what is on the right is emitter, and what is in the middle is base. So, this is collector left and this is emitter right and this is base. So, we will be connecting this transistor into the breadboard in 3 different lines. They do not have to be connected to each other. So, they will be connected in 3 different lines. So, you can see the collector is here. So, all these points are connected to each other. Anything I put here will get connected to the collector. Similarly, this is the base and this line, all these 5 holes here, they are connected to each other, and this anything I connect here, they will be get connected to this, and similarly this is emitter. Okay. So, let us do this input biasing circuit. With the base, we have to connect 120 kilo ohm resistance with the base. So, with the base. Okay. So, one end of the resistance is connected here, and then where does the other end go? That will go to the variable power supply here. So, something has to be connected from here to here. So, you can put it in any of the holes. All right. So, from this line you take that a wire, a long wire, this one, let us take this one, put it in one of these holes. So, from the resistance we are connecting, correct. So, from the resistance we have connected this, and if I put it here, that will mean, and when the battery is connected, that will mean I am taking voltage from this much, and when I vary this clip here, the biasing voltage will change. So, that is it. So, our this side is complete. The negative of the battery has to be connected to the 0 potential line. So, let me put it this way. Okay. Let me put it this way, it will be easier. So, negative of the battery should be connected to 0 potential line. So, this is the battery negative, this should go to the ground. So, connect this thing to ground. Good. So, this is our ground line, this is our 0 potential line, and this gets connected to the negative of the battery. Okay. So, the input side is complete. I have the base. From the base, I have added 120 kilo ohm of resistance. From there, I have added this variable point, which I will be connecting somewhere, and then this will be our input voltage. Okay. Now, emitter has to be connected to the ground. So, where is emitter? This one is emitter, this one is emitter. So, this should be connected to the ground. Good. So, this is the emitter, and on the same line along the width we have added this. So, this emitter gets connected to this point, and this point is connected to this ground 0 potential line. So, emitter part is over. Now, let us come to the collector part. From the collector we have to add 10 kilo ohm resistance. So, where is the collector? Collector is here, collector is here. So, in that same line you have to add a 10 kilo ohm resistance, and the 10 kilo ohm resistance should go to 9 volt battery. So, let us make a 9 volt battery line. So, where is the battery? 9 volt battery, keep it here, keep that 9 volt battery here. The negative of the battery should be connected to the ground. And positive of the battery you can connect to somewhere, say here, you put a line. Good. So, this is our 9 volt line. So, this point, this whole line here, this whole line here becomes 9 volt. Okay. This whole, all these holes are at 9 volts. Fine. So, the collector has to be connected to the resistance that you have done, and the other part of the resistance should get connected to this line somewhere. So, you can join it anywhere you like, you can join it here. And then from here, very good. So, you understand the working of the breadboard. This positive of the battery is joined here, but these are all internally connected. So, that 9 volt which is here, it is also coming here, and from here I am going to this point, and then these ones are internally connected. So, this 9 volt has been connected to this other end of the resistance. One of the end of the resistor is already connected to the collector. That part is done. The negative of the battery is already at ground. So, our output side is also complete. Now, we have to add the multimeters for measurements. So, one multimeter is needed for that input side. So, the black terminal should go to the ground 0. Yeah, the black terminal is going to 0. Good. And then the red one should go to that variable point. Where is that variable point? Here. So, that red terminal should be connected here. Okay, fine, fine. From the base it goes to 120 kilo ohm, and from the 120 kilo ohm it is going to the voltage, and that voltage, this variable voltage, the variable voltage base biasing voltage, that is being measured by this red wire, this clip here, this red wire here, and it is going into the multimeter. Okay. So, this is it. Then the output side. In the output side, once again the black terminal should be grounded, 0 potential. So, see how the circuit is implemented nicely. So, this is also at the same potential. So, all those negative terminals, all those black leads of these, they are joined together. Here they are all joined together. Okay. And the positive and the red terminal should be measuring VO, the collector. So, it has to be directly connected to the collector. And you can connect your this thing here, right. So, now it is connected to the collector. Okay. So, the circuit is complete. So, let us start working on this. So, this 1.5 volt battery I am now connecting, all right, and put this in DC voltage 2 volts range, and the other one output 20 volts range. So, I have not given any bias voltage, but you can see the output is 9.35 volt. Okay. That is natural, there is no bias volt. So, there is no base current, there is no collector current, and therefore, whatever is the voltage of the battery positive, that appears at that VO point, and that is 9.34. So, now let us start giving some bias. So, now I will be connecting this clip somewhere. Where is the 0? This is the 0. So, if I connect it very close to it, I will be giving very small bias. So, let me connect it here. So, you can see I have given some bias, approximately 0.15, 0.152 like that, and the output is still 9.34. It was 9.34 before this biasing, it is still 9.34 because it is in cutoff region. I have given a small biasing voltage, but that small biasing voltage is not able to sufficiently forward bias this base emitter junction, and you do not have significant injection of charge carriers, and the collector current is still 0 at the biasing voltage of 0.153. Let me increase the biasing voltage. So, I put the clip here. Now, what is the scenario? The biasing voltage has been increased. It is 0.276 or so, 0.275. But the output voltage is still 9.34. It is still in the cutoff region. The transistor is in cutoff region. Your base emitter junction is not sufficiently forward biased. So, let us go ahead. And now you see 0.549, and this output voltage has gone down from 9.34 volts, it is now 9.08 volts. So, that curved part on this VOVI diagram has started. Okay. So, we are moving towards that active region. So, the transistor is now conducting, the collector is doing some job, there are carrier injections from the emitter to the base, there is some IC, and there is some RL into IC drop on that 10 kilo ohm resistance, and therefore, the output voltage of the collector has gone little bit down. Again, increase it further. If I increase it further, what happens? See, The base voltage is now 0.623, not base voltage, the input voltage is 0.622 volts. Remember, after that you have 120 kilo ohm of resistance, there is a current IB there, there is a drop on this, this 120 kilo ohm. So, what reaches base will be very small, will be a fraction of voltage, 0.2, 0.3, 0.15 type volts there on the base. But the input voltage that I am supplying from my battery, from my 1 volt, this potential divider that I had made, that is 0.620 at this time, and the collector voltage is 8.26. So, it is going down, it is going down. So, now we are reaching that region, active region. Go further. .690 and 7.03. So, you see, as I am increasing this input voltage, this output voltage is gradually decreasing, as it should do in the active region. So, now let me increase the base voltage sufficiently, and let us say if we can go in saturation region. So, here you see the input voltage V I is 1.113 and the output voltage has dropped to 0.15, right. So, from 1.115, let me increase it further. Here 1.268 input voltage, but output is still 0.12. And here see, it is 1.302 and the output is still 0.12. So, this is the saturation region.